right. All right. So good evening. On the last one, boring you again with continuous waves from neutron stars. My name is Gianluca. I'm supervised by Maria Alessandra Papa. I'm a PhD student at the AI in NOFA. So I'm really glad that Anjana basically did the job for me. So he introduced you to the topic, so I don't have to go through this again. I'm just gonna, I hope this works. Doesn't crashes. No, it doesn't work. Well, imagine that you have an animation there and you're seeing a non-axis symmetrically deformed object that as it spins around its axis, it's emitting a continuous wave at frequency, which is double the spin frequency of the object. Of course, you saw that. It was an amazing animation. I took one night to do that and it doesn't work. All right. So Anjana has also partly mentioned why we haven't detected this kind of signals so far. And the reason is that it is very hard. These signals are extremely weak. And the reason why we madly keep looking for this is that they're continuous. So continuous wave is continuously hitting the detector. So basically, you can, in principle, build up signal to noise ratio and basically hope to detect it. However, this comes with huge computational costs. And so in general, our searches are computationally limited. And for the sake of completeness, here I'm using that epsilon parameter that was introduced before. It's exactly the same. It's called ellipticity, and basically it's the degree of non-axis symmetry, which I will loosely refer to here as deformation. So basically, based on this last fact that I said, our work is intended to be basically a first step towards the direction of optimizing all-scale searches. So differently than what Anjana has told you about, all-scale searches are blind surveys looking for continuous gravitational waves in the galaxy, coming from some galactic neutron stars. So what we did here was trying to model the galactic neutron star population, making use of a synthetic data set, basically trying to assess different things, such as trying to understand what we've done so far in terms of putting constraints in the galactic population. What kind of astrophysical objects are we hoping to detect at current sensitivity? Where in parameter space should we focus our attention? And how does the picture changes as we move towards future generation detectors? So the building up of this synthetic data set is done basically in two steps. A first step where we consider galactic remnant population, dynamically evolve it throughout the galaxy under the influence of the galactic potential, and having a present time distribution of neutron stars. And a second step where we actually try to translate the age of the object into spin and possibly spin downs. And in order to do this in our work, we assume that each neutron star was both magnetized and deformed. So for magnetic fields, we considered two very different models, what we call agnostic model and what we call empirical model. In agnostic model, we considered fairly uninformed priors that in the range of validity of values that pertains to normal, non-recycled neutron stars. Whilst with the empirical model, basically we retrieve distributions of magnetic fields and Earth spin frequencies that are consistent with the neutron stars that have been observed today, and these people try to basically reconstruct these distributions, taking in consideration all different manifestations of neutron stars. So for the ellipticity, we considered as well two main different models. A model one ellipticity, where the ellipticity stems only from the magnetic field, and in model two ellipticity, where instead this magnetically induced ellipticity is only a minimum value, and we actually log uniformly distribute this deformation from such minimum value up to the theoretical maximum upper value of 10 to the minus 5. So I can already show you our main results. So here in this table, you see, it's a little bit depressing, I'm sorry. So not much. So from model 1 ellipticity, we see something that we were expecting, no detectable objects from in 100 realizations. However, we see a few objects from model 2 ellipticity. And if we look a little bit more closely to the characteristics of these objects, you see this plot here. In the x-axis, you have magnetic field. In the y-axis, you have ellipticity. So basically, I binned this two-dimensional parameter plot space, and basically the lighter the color is, the more objects fall in that parameter space portion. And basically, what you see is something that we were expecting. Of course, the most favorable combination for current detectability is low magnetic fields, high ellipticity. And you see, as we move towards higher values of magnetic fields, what happens is that we quickly must hope for the highest possible ellipticity values to be realized in nature in order to have a current detection. All right. So here, in this plot here, you see how does the parameter space compare surveyed so far compares to what happens to be currently detectable and close to be currently detectable. Basically, we are surveying most of the interesting parameter space portion. We can maybe localize some areas where, in principle, we can just reject. However, this must be done carefully in the sense that we must understand what would be the sensitivity gain in rejecting that parameter space portion. And we're actually working on this, trying to set up a framework that optimizes all-scale surveys. Another interesting thing that I can show you in this table is that as we move from current sensitivity to more sensitive detectors, what you see is that currently you see here, I've just divided the entire band into low, mid, and high band. Currently, the high band still plays a major role compared to the low band, but as we move towards more sensitive data, I would say, the thing swaps. And it just, I'm going to show you very quickly that this is exactly what I'm talking about. When I consider third generation detectors, we have instead the low band that plays a more interesting role than does the high band. So in future of third generation detectors, we also see that basically only pushing down the lower frequency value from 20 hertz to 5 hertz, the increase in number of objects in band is 20-fold. This was also expected because basically the spin down is a function of some power of the spin frequency. So basically objects tend to stay in lower frequencies for longer. So here there was previously shown this table here. These are our results for third generation detectors. Again, from model 1 ellipticity, no detectable sources in 100 realizations. However, you see that model 2 ellipticity has about a factor of between 200 and 300 more objects compared to the current sensitivity one. This, of course, is in line with the fact that future generation detectors are around 10 times more sensitive. And so basically, you have to square this value because your horizon goes linearly with this value. And basically, if you assume that all objects stay in a disk, you have 10 to the square number of objects more to survey. This was already shown. The most interesting thing with third generation detectors for me is that those things that are called empirical models start to become detectable. So in that plot there, you can interpret easily just thinking that everything that is above the third generation line, which is the sensitivity, is detectable. And what we also found is that basically most of the detectable objects are extremely old and low magnetized neutron star. And this was possible because in this model, we actually account for magnetic field decay. So I finish here because I think I ran out of time, and I'll leave you with this. I just want to stress the fact that in view of third generation detectors, the fact that our empirical models become detectable is extremely interesting because they are basically built from observations in the M spectrum. And so the fact that this will be furtherly refined means that in future, when we use this data, we can practically constrain what is the last parameter we can constrain and EM observation scale, which is ellipticity, but in a galactic scale and not for a single object individually. So that's it.
Any questions?
I mean, if you say one of the points says third generation detectors are able to detect few hundred more sources than the current one. So current is 0.
Yeah, current is 0. Yeah, you're right.
So 100 times 0 is again 0.
That's true. Yes, you're right. So that factor is comparing what model gives us currently detectable sources. So that, of course, loses meaning if you say that by 04 there's 0 and 0 times 1 trillion is still 0. I agree on that. Yeah.
Unfortunately, I think the number is clear. It's decreasing sensitivity.
Yes.
Question from the back?
So there's stochastic background limit, right, from the Galactic Center, for example. Maybe there's 10,000 or there's 10,000.
I cannot answer to this question. But your question is, would the stochastic gravitational background limit our possibility to discriminate signal from signal?
What would imply for your realization?
All right.
Is it consistent with the realization?
Yeah. So I don't know. As far as maybe some people can know better than me, I think at the frequencies we work on, it's not really a big issue. However, I take my reply just as someone that is not an expert on this topic, so I don't know.
We have templates for independent social psychiatry, and then these templates are uniquely defined by the parameter, but I think background is not a determinant. So
In this case, you have realization, so he can predict the background. Or predict.
Oh, you mean like I can calculate that? Yes,
Yeah.
I haven't done that.
Yeah.
Any more questions for our speakers? So I have one question for you. So the magnetic field and ellipticity correlate. So let's say you have a system that has quite a large ellipticity. Intuitively, you would assume that perhaps this would be easier to detect, but if it's also coupled to a large magnetic field, it's more difficult to.
Yeah. But that's
Yeah.
So that's the reason why. So your question is for magnetically induced ellipticity, let's say, a high magnetic field would would result in a high ellipticity, but we see nothing. And the reason is that the higher the magnetic field is, it's true that the higher the ellipticity is, but the spin down is way quicker. So the permanence in band of that source is very, very short. Of course, that has some, I didn't go through the detail of this formula here, but you see here that the lambda parameter. So basically what happens is that with that lambda parameter, we could basically connect the colloidal component, so the one that is the portion of the magnetic field that is responsible for the spin down, with the actual deformation. That is actually not entirely correct, because the deformation is triggered by the magnetic field inside. So basically, we also calculated what should be that lambda value that would give us detectable sources, so they stay in band long enough for us to detect them, but at the same time do not spin the, have enough ellipticity values. And that lambda is something like 10⁻⁶. which if you look in in the literature is not thought to be correct line.